Hello guys, today we're gonna talk about robotic linear algebra, and my name is Lee Sering Thai and I'm from M241 linear algebra section 1. Uh, let's talk about the history of robotic. In 1981, the US space shuttle Columbian blasted off and equipped with a device called the SRMS, which stands for Shuttle Remote Manipulator System. It is a robotic arm, also known as canard arm, which proved to be a vital tool in all subsequent space shuttle missions, providing strong yet precise and delicate handling of its payloads. Its purpose is to place satellites into their proper orbit and retrieve malfunction ones for repair, and also critical repair on the shuttles. Since 1998, it has played an important role in the assembly of International Space Station. Let's talk about a robotic arm. A robotic arm consists of a series of links of fixed length connected at joint where they can rotate. Each link can rotate in space or be translated parallel to itself or moved by a combination of rotations and translations. To be able to design a mathematical model for the robotic arm, we must understand the rotations and translation work in the composition. To help ease the explanation, let's assume that the arm is in R2. From section 3.6 linear algebra, we saw that the matrix of rotation R about the origin through an angle alpha is linear algebra transformation matrix of cos alpha sin alpha minus sin alpha cos alpha. If V equal to a matrix A and B, and then translation along V is the transformation. T of x equal x plus b, or equivalently T matrix of x and y equal matrix x plus a y plus b. This is a graph showing the rotation, and this is a graph showing translation. Unfortunately, translation is not a linear transformation because T of 0 does not equal to 0. However, there is a trick that will get us around this problem. We can represent vector equal matrix of x and y as the vector is in R3. This is called the representing x in the homogeneous coordinates. Then the metric multiplication, which 0 times x, 0, 1 times x, 0 times y, a times 1, which got x plus a, 0 times x, 1 plus times y, b times 1, which got y plus b, and then 0 times x, 0 times y, 1 times 1, which was 1. Then the matrix represents the translated vector t of x in the homogeneous coordinates. We can treat rotations in the homogeneous coordinates. Also, the metric multiplication is cos alpha times x minus sine alpha times y, 0 times 1, which got x cos alpha minus y sin alpha. Sin alpha times x cos times y, 0 times 1, which x sin alpha plus y cos alpha, and then 0 times 1, 0 is 0 times x, 0 times y, 1 times 1, which you get 1, which the metric represents the rotation vector of our x in the homogeneous coordinates. The combination of t times r that give the rotation r followed by the translation. This is now represented by the products 1 times cos alpha, 0 times sine alpha, a times 0, which you got cos alpha, and then 1 times minus sin alpha, 0 times cos alpha, a times 0, which got minus sin alpha, and then 1 times 0, we got 0, 0 times 0, a times 1, which got a, and then the second row, 0 times cos alpha, 1 times sin alpha, and then b times 0, which got sin alpha, and then 0 times minus sin alpha, 0, 1 times cos alpha is cos alpha, and then b times 0 is 0, which we got cos alpha, and then 0 times 0, 1 times 0, b times 1, which got b, and then 0 times cos alpha, 0, 0 times sin alpha, 0, 1 times 1 is 0, so we got 0, and then 0 times minus sin alpha is 0, cos 0 times cos alpha, 0, 1 times 0, we got 0, and then 0 times 0, 0 times 0, 1 times 1, which is 1, which is called 1. Let's take a note that t of r does not equal r of t. Opposite does not equal to each other. To model a robotic arm, we give each link its own coordinate system. It's called a frame and examine how one link move in the relation to those of which is directly connected. To be specific, we let coordinate x or the links a and I be x of I and y of I, which the x of I is axis aligned with link, and the length of the a of I is denoted by an a of I, and the angle between x of I and x of I minus 1 is denoted by alpha of I. The joint between a of I and a of I minus 1 is a point 0, 0 relative to a of I, and a which coordinates a of I minus 1, 0 relative to a of I minus 1. Hence, the relative a of I minus 1, the coordinate system of a of I have been rotated through alpha of I and then translated along the matrix a of I minus 1, 0. This transformation is represented in homogeneous coordinate by the matrix. Considering the figure of A, it shows an arm with a 3 link in which a of 1 is in its initial position. Then each of the other 2 links have been rotated 45 degrees from the previous link, and we take the length of each link to be 2 units. Well, figure B shows that A3 is in international frame. The transformation is T of 3 is cos 45 minus sin 45, 2 sin 45 cos 45, 0, 0, 0, 0, 1, which we get 1 over root of 2, and minus 1 over root of 2 is 2, 1 over root of 2, 1 over root of 2, 0, then 0, 0, 0. Cause its rotation 45 degrees and then translate by 2 units, as we can see. Well, as a figure shown in the figure C, this is place A3 and in appropriate position related to A2, A of 2's frame. Next transformation, T of 2 equal to cos 45 minus sin 45, sin 45 cos 45, 0, 0, 0, 0, 1, 1 over root 2 minus 1 over root 2, 2, 1 over root 2, 1 over root 2, 0, 0, 0 is applied to the previous result. This place both of A of 3 and A of 2 is in the correct position relative to A of 1 as shown in figure D, same as each other. Normally the third transformation T of 1 will be applied to the previous result, but in our case T of 1 is the identity transformation because A of 1 stays in initial position. Well, typically we want to know the coordinates of the hands of the robotic arm. Given the length and angle parameter, this known as the forward kinetic, will follow the sequence of calculation above. We see that this is 3 link chain, and then this A3 is in the initial frame, then T3 put A3 in the A2's initial frame, then D and D2 and D3 put A3 in A1 initial frame. Now we need to determine where point 2 of 0 and up after T of 3 and T of 2 have applied. Thus the arm is in T of 2, T of 3, measure of 2 and 0, 1, which we got is the same thing, so which we say 1 over root of 2 minus 1 over root 2, 2, 1 over root 2, 1 over root 2, 0, 0, 0, which power of 2, and then the matrix 2, 0, 1, and then which we multiply each other, we got 0 minus 1, 2 plus root of 2, 1, 0, root of 2, 0, 0, 0, 1, which now multiply with 2, 0, 1, which we will get 2 plus root of 2, 2 plus root of 2, 1. The matrix will represent the point 2 plus root of 2 or 2.2 in the homogeneous coordinate. It's easily checked from figure A that is correct, which is the same. Well, the method is used in this example generalized in robotic arm in 3 dimensions, although in R3 there are more degree of freedom and hence more variables. This method of homogeneous coordinate is also useful in other applications, notably is in the computer graphic. Well, I have finished and thank you for listening.